This video is an introduction to VSEPR theory. VSEPR theory is a set of rules that we can use to look at a two-dimensional Lewis structure of a molecule and figure out what the molecule would look like in 3 dimensions, like this. Because molecules are like actually things in real life, so they'd have 3-dimensional structures that are often more complex than we can draw in 2 dimensions here. So let's start, take a look at some Lewis structures and figure out what the 3D shapes of those molecules would be. Here's our first example, beryllium dichloride. We got a beryllium atom, it's a central atom, surrounded by chlorines on either side. Note that beryllium here is an exception to the octet rule, which means that it's happy to have fewer than 8 electrons in its valence shell. When beryllium is making 2 bonds, like it does here with chlorine, it has only 4 electrons in its valence shell, and it's perfectly happy with that. So just keep it in mind, but it doesn't have any important bearing on what the VSEPR shape is. So, a little bit about the VSEPR rules here. VSEPR stands for valence shell electron pair repulsion, which is a really fancy way of saying that electrons or pairs of electrons want to push away from each other and want to be as far away as possible from each other. And that kind of makes sense because electrons have negative charges, so opposite charges repel, and obviously these things are going to want to be far away from each other. Let's look at what bearing this has on the 3-dimensional shape of a molecule. So in beryllium here, where are these valence shell electrons that want to push away from each other? Well, the valence shell electrons are in these bonds. I've often said that you can think about covalent bonds as if they're hands from the atoms with electron pairs, and that these hands are connected because they're both holding on, they're both sharing this pair of electrons. So we could draw beryllium dichloride like this, where we have a hand from the beryllium, a hand from the chlorine coming together to share this pair of electrons. So this just reinforces the idea that there is a pair of electrons in each one of these bonds that's shared between the atoms. Okay? So, as we said from VSEPR, these electrons want to be as far away from each other as possible. They want to repel. So, how is this going to influence the 3D shape of this molecule? How can these bonds arrange themselves in 3D so that they are as far away from each other as possible? The 3-dimensional shape of beryllium dichloride is going to look like this. We've got a beryllium here in the middle, and then we have these 2 chlorines on either side, and all 3 atoms form a line. They're all in a row here, a straight row. We call this a linear molecule, which means line, so that kind of makes sense. And let's look at the angles here. The angles between these 2 bonds are going to be 180 degrees. So 180 degrees between these 2 bonds is how the electrons that are in these 2 bonds, it's how they can be as far away from each other as possible. So we can say that this linear shape that we have here is the way that 2 things are going to surround themselves around a central atom. The central atom is here, then we've got these 2 things that are 2 bonds, and the 2 bonds are as far from each other as possible in this linear shape. Now, in beryllium dichloride, I'm talking about single bonds here. But it actually doesn't matter whether we've got double bonds or triple bonds. For example, CO2 has a shape like this, where there's a double bond here and a double bond here. But there are electrons in both of these bonds. And so each one of these double bonds, they just count as a bond. So for CO2, I still consider it as just 2 things around a central atom. So CO2, it's going to have this linear shape here too. This will be the carbon, and these will be the 2 oxygens. They'll be 180 degrees apart. So double bonds, don't worry, it's just 2 things, 1, 2, around a central atom. Okay? Just to drive this point home, Triple bonds, it's the same thing. Got a triple bond here, a single bond here. I just consider this to be two things around a central atom. 1, 2, so HCN is going to have this linear shape as well, with these two bonds being 180 degrees apart. So we always get a linear molecule, 180 degrees, whenever we have just two things surrounding a central atom. Now let's take a look at some molecules where we have three things that are surrounding a central atom. Here in BF3, I have a central atom surrounded by three bonds to other atoms. And in this case, boron, like beryllium before, is an exception to the octet rule. Here, boron, when it's making three bonds, has 6 valence electrons. It's totally happy with that. So, as I said earlier when we were talking about beryllium, is that we can think about these bonds between the boron and the fluorine here as hands that are sharing an electron pair. And the electron pairs in each one of these bonds push against each other, and they want to be far away. So, when we have three things, the electron pairs in these three bonds, how do we arrange these so that they are as far away from each other as possible in 3D? The molecule is going to look like this. I'm going to have these three atoms, 1, 2, 3, surrounding a central atom, and I'm going to get the shape called trigonal planar. The trigonal comes from the fact that there are 1, 2, 3 things. That's just what trigonal means. And planar, because take a look at this. These atoms are all arranged in this plane, all right? They're all in a straight plane here. Now, what are the angles between the atoms in a trigonal planar shape? They are all 120 degrees. So the angle between here and here is 120, here and here, and here and here. So that is what BF3 would look like in 3 dimensions. Now, just as before, it doesn't matter whether we're talking about double bonds, single bonds, triple bonds, it's all the same. Okay, so in CH2O here, I have 3 things surrounding the central atom. I got a double bond, a single bond, and a single bond, but it's still just 3 things that want to be as far from each other as possible. So that means that CH2O here is going to have the same shape in 3 dimensions as BF3 does. It's going to be a trigonal planar molecule with 180 degrees between each pair of bonds. Now, the next thing we're going to do is we're going to look at some molecules that have 3 things around them, okay? But these 3 things are not all bonds. Here's an example of this. SO2, okay? It's got 3 things around this central atom. It's got a bond here, that's 1 thing. A double bond here, that's 2 things. But then it's got this unshared electron pair up here. These 3 things all have electrons in them, so they all want to push away from each other. So what shape is SO2 going to have in 3 dimensions? If you think it's linear, and the 3 of these atoms are all lined up in a row, that's not right, because you're not taking this unshared electron pair into account. To figure out the shape of this, let's go back to this trigonal planar molecule, okay? In this trigonal planar molecule, we had 3 things around a central atom. It's just they were all other atoms, okay? So this is how you arrange 3 things around a central atom to be far away from each other. Now, in SO2, we're going to get a shape that's very similar, except it's that one of these atoms from the trigonal planar shape is going to have been replaced by an unshared electron pair. But otherwise, look at how similar they are, okay? It's atom, 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 atom. It's just this atom here has been replaced by this unshared electron pair. But these atoms are still in the same place because this unshared electron pair pushes the atoms away from each other, just like this atom did, okay? So they're based on the same shape, 3 things around a central atom. It's just one of these from the trigonal planar shape has been replaced by an unshared electron pair, okay? So this molecule here, we call this a bent molecule because instead of being in a straight line, the atoms are arranged in this kind of bent shape. Looks like someone just grabbed it and bent it like that. So, what are the angles going to look like in the bent molecule? Well, in the trigonal planar molecule over here, when you have 3 atoms, the angles between any 2 bonds were 120 degrees. In the bent molecule, though, it turns out that this unshared electron pair here pushes harder against these 2 atoms than the atom up here would, okay? And so that means that the angle between these 2 bonds is going to be a little bit less than 120 because the atoms are getting pushed closer together. It's going to be less than 120. It's going to be more like about 116 degrees between the 2 of these, just once again because this unshared electron pair is pushing harder than this atom. So instead of 120, they're pushed harder, pushed closer together, and it's more like 116. But here's the point. We get the bent molecule when one of these 3 atoms from the trigonal planar is replaced by a lone electron pair. So always keep your eye on these lone electron pairs because they have a very significant impact on the shape that a molecule is going to end up having. Now let's move on to some molecules that have 4 things around the central atom. CH4 here has 4 things around a central atom, and they are all bonds to other atoms. So each of these bonds contain a pair of shared electrons, and that means that the bonds all want to push against each other and be as far from each other as possible. This molecule, CH4, is going to have this shape in 3 dimensions, okay? This is called a tetrahedral shape, and it's how you arrange 4 bonds as far away from each other in 3D as possible, okay? Tetrahedral. And in the tetrahedral molecule, there are 109.5 degrees between any 2 bonds that are next to each other in this molecule. So 109.5 here, 109.5, and so on. So 4 things around a central atom, you get a tetrahedral shape with 109.5 degrees between each bond. Now NH3 here also has 4 things around a central atom, but not all of them are bonds to other atoms. Okay, so we have 1, 2, 3 bonds, and then a 4th thing that's a lone electron pair. So what's its shape going to look like in 3 dimensions? I'm going to go back to this tetrahedral shape for just a minute because this is how we arrange 4 things around a central atom when they're all other atoms, okay? But in this shape, they're not all other atoms, okay? So NH3 is going to end up having this shape, which is called a trigonal pyramidal shape. Look at how similar it is to the tetrahedral shape, okay? I'm sort of showing them on their sides here. It's just that the atom that was up here when we had 4 atoms around the central atom has been replaced by an unshared electron pair here, okay? So we've got 3 atoms. 3 atoms are the same between this, and it's just this atom has been replaced by an unshared electron pair. So this has a shape that we call trigonal pyramidal, and we call it trigonal pyramidal because if you look at it from its side, it kind of looks like a pyramid. Okay, got these 3 atoms pointing down. All right, now for angles in the, I don't know quite where to put this, so I'll kind of put it up here, I guess. For atoms in the trigonal pyramidal, for angles in the trigonal pyramidal molecule, we'll remember that in the tetrahedral we have 109.5 degrees between all of the bonds. But in a trigonal pyramidal, just like we saw with the bent molecule, the unshared electron pair here pushes a little harder against these 2 bonds than an atom would. And so that means that the angle between these bonds is pushed a little tighter, and so it's smaller than 109.5. For a trigonal pyramidal molecule like NH3, the bond angle is more like 107 degrees, a little less than 109.5 degrees. So 4 things, if you have 4 things around a central atom, but 3 of them are bonds and 1 of them is a lone electron pair, you end up with a shape that's called trigonal pyramidal that looks like this. Okay, one more example and then we're done with the VSEPR video. Here's the last molecule we're going to look at, water, H2O. Okay? This thing has 4 things around a central atom. 2 of them are bonds, 1, 2, and 2 of them are lone electron pairs, 1, 2. So what's its 3D shape going to look like? How can we arrange these 4 things as far away from each other as possible in 3 dimensions? As before, I'm going to look back at my tetrahedral molecule, which shows how I arrange 4 atoms or 4 bonds as far away from each other as possible in 3D. For H2O, though, only 2 of the 4 things are bonds. The other 2 are lone electron pairs. Okay? So that means that I'm going to end up with a shape like this. Okay? I've got my 2 atoms down here, hydrogen and hydrogen, but then I've got my 2 lone electron pairs up here. Look at how this is similar to the tetrahedral molecule if I look at them from the side. Okay? I've got atom, atom, and atom, and atom. Okay? It's just these 2 atoms from the tetrahedral molecule have been replaced by these 2 lone electron pairs from the water molecule, these unshared electron pairs on the oxygen here. Okay? So look at that from the top, how they have very similar structures. It's just these 2 are missing, and they've been replaced by the lone electron pairs. We say that this molecule has a bent shape because these atoms here are not in a straight line, but they're bent like this. Now, what are the angles here? Let's look at the tetrahedral again, which had 109.5. Then in the trigonal pyramidal, when we had 1 electron pair, it pushed the bonds a little bit closer together, so we had about 107 degrees between them, a little less than 109.5. Now when we have bent, instead of 1 unshared electron pair, like in the trigonal planar, I have 2 lone electron pairs. And so the combination of those 2 is going to push the atoms even a little bit closer. So in a bent molecule like water, the angle between them is going to be 105 degrees, about 105 degrees, which is less than 107, which is less than 109.5. So the more unshared electron pairs you add, the tighter the 2 or more atoms get pushed together. Okay, so if you've got 2 bonds and 2 lone electron pairs around a central atom, you're going to have this bent shape. Now there's just one thing that I want to say about this bent shape. Okay? There are 2 ways that we can get a molecule with a bent shape, but they're different. Okay? We can get a bent shape when we have 3 things around a central atom, and 1 of them is an unshared electron pair. Then we get something like SO2, where we have something that's a little less than 120 degrees between these. Another way to get a bent shape is when we have 4 things around a central atom, but 2 of them are lone electron pairs. And in that case, because we have 4 things, everything's a little tighter, we have an angle of 105 degrees that's a little less than 109.5. So you just finished watching this VSEPR video. Where should you go from here? Well, the first thing that it's important to know is that there's a difference between watching the video and actually being able to look at a Lewis structure and figure out what the 3D shape of that molecule would be. So the first video that you should watch is this VSEPR practice problems video, where we'll go through a whole bunch of Lewis structures and go through the steps to figure out what the 3-dimensional shapes will be. So that's definitely the next thing you should watch. Now, there are some common mistakes that students often make when they're learning VSEPR. So I made a video on that. It's called VSEPR Common Mistakes. Watch that after you've done the practice problems to make sure that you're not falling into any of the common traps that tend to trip people up when they're learning VSEPR. Now, maybe this is all of the stuff that you have to learn for VSEPR, and this is everything up to molecules that have 4 things around a central atom. But, depending on what you have to know, you might have to know molecules where there are 5 things like this around the central atom, or where there are 6 things like this around a central atom. So I made some other videos on this sort of stuff, okay? I made a video on the trigonal bipyramidal family, which are all of the molecules that have 5 things around a central atom. And then there's another video on the octahedral family, which are the molecules that all have 6 things around a central atom. And now finally, after you've watched the video on the trigonal, bipyramidal, and the octahedral, you can do the VSEPR practice problems for these advanced structures where you'll go over the molecule shapes that I talk about in this video, So this might look like a lot, but if you go through it, it should really give you a solid foundation with this 3-dimensional VSEPR stuff.